I'm Judy Walker. I'm chair of the UNL Department of Mathematics. It's my pleasure to introduce our speaker this afternoon, Professor Michael Hopkins. Professor Hopkins is a leader in the field of homotopy theory and one of the top mathematicians of our time. He's been on the faculty at Princeton, Chicago, MIT, and since 2005, Harvard. Among his many awards are a Sloan Fellowship, membership in the American Academy of Arts and Sciences, foreign membership in the Royal Danish Academy of Sciences and Letters, and membership in the National Academy of Sciences. Mike's an Omaha native. He's even a member of the West Side High School Hall of Fame, along with Nick Nolte. I've enjoyed getting to know him over the past few years as his relationship with our department has grown. This relationship was formalized about 2 years ago when we were able to appoint him as a visiting research professor. Through this appointment, he's been visiting us twice a year, giving workshops for our graduate students. The workshop from last fall was related to the most recent of Mike's many significant mathematical contributions, the Crevere invariant problem, a 50-year-old problem which Mike solved in 2009 in joint work with Mike Hill and Douglas Revenell. This proof was a big part of what led to Mike receiving the 2012 National Academy of Sciences Award in Mathematics. And he's currently working with a group of our graduate students and faculty to transform those lectures into a book on the subject. The Crevere invariant is one of many mathematical invariants. The topic of Mike's talk today is how invariants can help us know the answer in advance. Professor Hopkins.
Thank you, Judy. Judy promised not to embarrass me too much, so thank you. Are the mics live now, both of them? Okay, I'll watch what I say. So how many, I want to start out with something. How many of you have seen the movie The Matrix? Oh, good. I was worried for a minute. Okay, so you know, like there's this point in The Matrix where Neo's in this office and he gets a phone call, and then Professor Morbius, you know, calls him up, and he's got to dodge all these bullets. These guys are chasing him, and you don't know how Morbius can possibly be knowing who's going to be where and how he can get him out of the building alive. So I want to start with a reenactment of that, and I need some volunteers. I also want to. So I need someone to be Neo. Someone. Do you want to do that? Do you want to do it? Okay, come on. You can come up here. All right. That's good. You can leave the chair. Good. Okay. Just come up here for a minute. Okay. Just wait right there. And now I need someone to be Oh, don't here. Just move off that. Morpheus. Anyway, that guy. No one? The only thing this requires is that you can read. Okay. All right. Come on. Good. Okay. See these cards that say move?
Yes.
Just don't look at them. You're looking at them. No, just don't look at them and go over there. Just stand over there. And now I need someone to be the. So this one's tricky. I need someone that can be the explosions. So they have to be young enough to bend over and pick up the places where it's exploding, but they have to say boom. So it's a little bit better if they're like a boomer, you know, a little. So I need someone who's a boomer who can bend over and pick up stuff off the floor. Nobody? Okay. You are? Dude. Okay. All right. Come on. Yeah. Can I see some ID? All right. All right. That's good. All right. And you can hang on to these cards. All right. That's maybe enough volunteers. Okay. So here's the deal. Okay. So, oh yeah, did I tell you this? I'm going to combine this with the game of Clue. Okay. So you have to turn around. So these are some rooms in Clue, and you got to pick one of those. Okay. You're allowed to tell us.
Sunroom.
Okay, good. All right. So the sunroom. So Neo is starting off in the sunroom. So find the one there that says sunroom and stand on it. Okay, so now these are all the rooms of the house in Clue, and you don't have to, you're going to be focused down here. This is just so that they can see what you're doing. And I'm going to use this, this laser pointer. Is this set on stun or kill, Judy? Kill? Okay, okay. So I'm going to use that and, oh, ow, okay, and point, and he's in the sunroom right now. Okay, so here's the deal. Morbius is going to look at the top card. Oh, no, the top one. Oh, yeah, that's it. And then you're going to say move, and then that's how many he's supposed to move. So go ahead.
Move.
And then turn it over, and there's a number on the right. No, oh, wait, no, wait. No, sorry, you.
Oh, okay.
Okay, move 3.
Move 3.
Okay, now you get to move 3, but you have to go, like, it's got to be realistic. Like you're going, rooms don't have doors in the corner. So you can move 3, but 3 rooms, but you can, like, go that way, and then 2, 3. Good, okay, perfect. All right, now what room are you standing in?
The hall.
The hall. So he's down here in the hall, and now you're going to tell us what room that you're blowing up. The library. And okay, and now you're going to, so that's the simulating the library being destroyed. Oh, wait. You have to start here.
Okay.
Okay. So can we get some different volunteers? All right, okay. All right, good. Sunroom. So the sunroom was destroyed. So now you can use your youthful ability to bend over. Okay, so the sunroom is gone. There's no sunroom. Okay, excellent. Good. Oh, good. Okay. Okay. All right, so go ahead. Next one.
Move 5.
5. 1, 2, 3. Okay, where are you? He's down here in the lounge. All right, and what room? Well, so hang on. He's got these cards here, right? They were written in advance. They were passed down through the ages. They're mystical cards. These two, they were passed down to the ages just for this moment. And the computer doesn't know about them. The cards don't have any idea how, where he is, but somehow, well, what room blows up now?
The dining room.
The dining room. So you're safe. Okay, so you can take that up and go boom. All right. So that's okay, good. Right. So all right. So we're trying to get him out of the building again. So now Morpheus, how far does he have to move?
Call you and tell you to move 3.
3. So where are you standing now?
The library.
The library. And what blows up? Oh, sorry, I gave that away.
The kitchen.
The kitchen, right. He escaped again. So I have to emphasize, I mean, there's a computer involved, and so the NSA could know anything. But really, there's just what's written on these cards. This computer's here only so that you can see what he's doing. All right. What's the next phone call tell him to do?
Call you and tell you to move 4.
4.
1, 2, 3, 4.
Tough choice there at the end. And what blows up?
The lounge.
Lucky you weren't in the lounge. All right. The lounge blows up. Okay. Boom. Good. Okay. Excellent. Excellent. Now, what's that? Oh, that was good. Okay. Yeah. That was it. Sometimes they don't all go off. Okay. Next one.
Now move 7.
Okay. All right. Where are you?
The study.
So he moves 7 random places, and he finds himself in the study. And what room gets blown up?
The ballroom.
The ballroom. So you lucked out again, kid, because actually these are wired to this, and that's the billiard. That's the billiard room. Sorry. Yeah, that's okay. Good. Okay. All right. We're down to 4 rooms. That's getting. Thanks. Good. That'll work better. Good. Okay. Phone call.
Move 6.
6. That's good, because I know if I'd done that one last turn, I would have been dizzy for the rest of the day. So, what room are you in?
Study.
The study. And what blows up?
The hall.
Whew. Okay, that was lucky. Okay. You knew that would happen?
But you're around. I'm scared I will land on
It's scary, but nothing bad will happen, I promise. So, okay.
Move 3.
3. 3. All right. What room are you in?
The library.
He's in the library. And what room blows up?
The study.
The study. That was close. And now, so at this point, up until now, right, these missiles that we've been simulating, they had a less than 50-50 chance of actually hitting him. This could have just been blind luck. But now it's down to a 50-50 shot, right? And so what's he supposed to do?
Remove one.
Okay, that's hard to choose. All right, excellent. And what blows up?
The library.
The library. And you escaped through the billiard room. All right, so let's give this guy an applause. That was great. So when I was a kid, that's good, thanks. When I was a kid, there was this magician named David Copperfield, and he used to have these shows on TV, and he did this trick. He did this trick where it was done with cards, and you had to like point to a card on the screen, and he'd take away these cards. And well, let me ask you something. Did that feel like magic to you? It did, because most of the time when I do that, nobody leaves the room going, "Oh, it's a witch! It's a witch! It's a witch!" It doesn't really feel like magic. We were kind of annoyed as kids when David Copperfield did that. It didn't really feel like magic. It feels like something else is going on. I don't know. Is that your sense? Maybe you've all seen that before? Have people seen that before? You have. You saw. Well, you're my age, man. You saw David Copperfield, right? So. Right, it doesn't feel like a magic trick. You haven't sort of witnessed something that was sort of eye-popping and mysterious. It feels like there's something behind the scenes that's very systematic that's going on. And that's the thing I want to talk about. What's going on behind the scenes here is a mathematical invariant, a little piece of mathematics. And mathematicians, we have a sense. When we feel something like you just saw, we have a deep instinct that there's something going on, and we have organized ways that we investigate it. And so what I want to do today is, well, first I want to tell you what the invariant was here, and go through and tell you about some of the more important invariants in mathematics that kind of really cause mathematicians to really think deeply about some of the things that we study. So let me go back here. So I'm going to unexplode all those things, and instead of calling these rooms kitchen, ballroom, sunroom, blah, 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 I'm just going to number them. So instead of calling them names, let's give them numbers 1, 2, 3, 4, 5, 6. Now, what's the other thing I did? I showed my volunteer a list of rooms to choose from, but I didn't show him 9 possible rooms. I only showed him this many rooms. Now, do you notice anything about that? Can you see something special about the rooms that I let him choose from? They all have odd numbers. They're the odd numbered rooms, right? 1, 3, 5, 7, and 9. So out of all the possible rooms, I only let him pick an odd numbered room. And then, so when he was allowed to stand in this grid, he was only on one of the green squares. He was in an odd room. Now, my other rule was that you were not allowed to go diagonally. So that means every time you move, you change colors. So if you move an even number of times, you're going to be back on the same color. And if you move an odd number of times, you'll have switched colors. So the first thing I had him do was move. So he started out on a green one. I had him move an odd number. He moved 3. That puts him on a whatever color that is, salmon, and I erased a green one. And it just continued like that. All I was worried about was whether he was on an odd number or even, and I could rig that by telling him how many to move. So he's on a pink square, and I told him to move 5 the next time. That puts him on green, and I could blow up any of the pink squares I wanted to, and that's what I did. And we just worked our way down like that. So if it's hidden from you, if I don't call these even and odd, I call them something else, then it looks kind of mysterious. But really, there's a mathematical invariant going on behind it, which is the notion of the parity of a number. We're not looking at all the numbers, we're just looking at even or odd numbers. And so that doesn't quite parse like in English. An invariant is something that you can measure and it won't change that's unchanging, like the total energy in a system. But we use the name, we use that for focusing on something that's controlling the situation, but behind the scenes. So in this case, it was even and odd. If someone started on if he was on pink and I said move 6, he'd wind up on some other pink square, because every time he moved, he'd have to change colors. And that way I could rig it so that he wound up always safe. Okay, so now I want to do an experiment with everybody. I want to explain to you an invariant that was discovered in the 1700s in mathematics that played an extremely important role. And so I need so for this I need some volunteers as well, but I'll hand things out to people, and I need some round things, some balls. Unfortunately, there happen to be a bunch lying around in the room. So why don't let me someone can take one of these. You want to volunteer again? Okay, sure. All right. Good. Now don't pop it. And I'll take this one. I have a few more here. Here's some. Does somebody want one of these? Way back there. Here. Oh, that didn't work. Here, make sure that gets back to that guy. And someone else take another one. Now what we're going to do, oh, you need a pen too. That's all right. This will work better. Thanks. Wait, this isn't like a concert. Quit passing that thing around. So now we're going to do it with a Frisbee. All right, so here's a marker. Try it on your dad's shirt and make sure it works. No, don't do that. So, okay. Anybody else? Who has another balloon? Can I toss this to you? Thanks. Good. Wow, that was a good catch. Oh, sorry. I got excited. Okay. So what we're going to do now, we're going to mark these balls up. We're going to like play Farmville on these. Okay, so we're going to make farms on them. We're going to make, so how would I make a farm? I'm going to make a dot. You guys are going to do this, but I'll start here. And don't make a lot of them, because you're going to have to count something when I'm done. So when you're done. So I'm going to make my farm, I'll make a big dot for a fence post. So there'll be one here. I'll put a fence post here. I'll put one here. And then I'm going to connect these with some fences. And for me, maybe I'll put another one way over there and connect them with fences. Okay, so now I have my ball, and it's been, I've put some farms on it. And so that's what I want you to do. My farms are basically triangle shaped, and they should be shaped roughly like that. So go ahead and do that. So go ahead, don't put a lot, because you're going to have to count some things. I see you already started. Okay, good. And now we're going to have to count some things. And some balls that you find in nature, like a basketball, I don't, from undersea, you ever watched the National Geographic Channel? Okay, so basketballs, they come with farms on them, well, so to speak, but they're broken up into, here's a post, right? And then I can think of this thing as a fence. So somebody needs to count the count, and a soccer ball is the same thing. A soccer ball, I've got some corners where I can think of fence posts. This would be like if the entire planet got together and decided to arrange things into hexagonal and pentagonal farms, but that's another example. So I need some people to, so I borrowed these, I don't want to mark them up, but I need some people to count the farms on those kind of balls. And I figured that at this point in the lecture, it was probably causing a lot of stress, all this calling on volunteers. So I got relaxable balls. So, so I don't know. Here's some. You can just pass these around. I don't know, but or should I just Here's a relaxable soccer ball. Here's a same guy. All right. How's the insurance for this? We're good. We're good. Okay. I don't know. Just like you want to just pass these around to people.
Can I throw them?
What's that? You can throw them as long as I don't poke any eyes out. I don't care. But try to make it relaxing. Okay. And the basketballs are a little funny, so I'm going to tell you how to count the basketball in a minute. So let's get these around, and you might need a pen. Okay, so you might need you know what? All right. Pass them around. Just take one and take a pen. We don't need to do that many. We don't need that many. Just one of each kind will really work. You're all done? Okay. That's good. No, hang on. Just hang on to it. You'll need to, you might need a pen, you might not. If you have a pen, let's just see how this goes. Okay, so, all right, that's good. Do you guys have pens? All right. All right, so here's the deal. Okay, that's good. That's fine. You're good. Okay, now what I want to do, so on your farm, where's my, here's my planet covered in farm. So I have fields, but I'm going to call those pastures. And first I want to count the number of those. So in my case, I'll just put a P in them. There's a pasture there. There's 1, 2, and then I've got one giant one at the back, 3. So that gives me 3 pastures. Okay. And then I have some fences, okay? All right, so in my case, there's 1, 2, 3, 4, 5 fences. And then, I shouldn't have called those pastures because what do you call fence posts? What's another name for fence posts that doesn't start with a P? FP? What? FP? Yeah. Wait, somebody else said stake? A stake? Okay. Okay. That's good, yeah. So we're staking out our farms, and now we're going to count the number of stakes. So let's call those S's. So in my case, I have 1, 2, 3 S's. Whew, I'm glad you said that, and you'll see why in a minute. 4 S's. Okay. Okay, so everybody figure out their own number for that. Their own number of faces, edges, of pastures, these, pastures, fences, and stakes. So a pasture is a region like that, a fence is like this, and a stake is that. I want you to, everybody figure out their number. Okay. So the basketball's a bit tricky. I can tell you that the worst one to do is a volleyball. I hope there weren't any in there, but that works too. You already done it? Do you need a pen? You just want to relax. Oh, you got it? Really?
I think there's 32 pastures and 60 stakes.
Okay. Well, all right. You think? That's okay. All right. No problem. Okay, so everybody's done that. Has everybody done that? Most people? And now what I want you to do is take I want you to take this number plus this number and subtract that number. So I want you to take P plus S minus F. So in that case, it's 3 plus 4, which is 7, minus 5, and that gives me 2. So let's see what other numbers we can get. Is anybody, you got 2 also. You got 2 also. What did you get? 2? This is good. This feels very political. But anybody else? You got 2 also? You got 2? So now the trick with a baseball, I forgot to say, is that you have to mark somewhere where there's a stake, because your fence has to have a stake. So count 1 stake, and then what do you get?
Then we would have 2 plus 1, so 3 minus. You got it.
2. Good. Thank you. Yeah, I forgot to say baseballs. You have to put a stake in the baseball. Okay. Anybody else want to report on their number? Okay, so this is kind of an amazing thing. Euler discovered this in the 1700s, that whenever you do this, well, this was before they invented balloons, but or soccer or basketball, or I don't know what he was thinking. But anyway, when Euler did this, he discovered that no matter what you do, you always get 2. No matter how you cover the earth in farms, and you do this, you're always going to get the number 2. So that's an invariant. That's something that no matter what you do, no matter how you perform this, it always comes out the same number 2. And that's kind of an amazing thing if you think about it. So mathematicians, when we encounter that, we want to really know what's going on. First of all, we want to know how could I prove that. But I'm not going to talk about proving it today. But the other thing, usually someone will figure out how to prove it. And in fact, Euler, his first proof was completely wrong. But then the other thing we want to figure out is what's it really an invariant of? Like, for instance, some of those balloons were white and some of them were yellow. So it clearly didn't depend on the color. It had something to do with the thing being the shape of a sphere. So that's good. Mathematicians want to figure that out. It might be a theorem about spheres, but what if it was, what if it was shaped like this, like my heart? I mean, what number do you think you'd get if we did this? 2. We get 2 again. And why is that?
Because topologically speaking, it's a sphere.
That's true. That's true. I was kind of, but also because, I mean, it's not really going to change things, right? If I kind of could blow this up even more without popping it so it came back into a sphere, it's not going to change the possible ways I could arrange a farm on it. So with this number, this I'll always get 2. So it's not, so it forced mathematicians to try to look at shapes in a different way. I mean, this was, like when I say I'm drawing a triangle, you don't think of one specific shape. Triangles come in many different sizes. It's like saying a number is even or odd. Many different numbers are even, many different numbers are odd. There's many different kinds of triangles, but there's something about them that we label the triangle. They have 3 edges and 3 vertices. And this we wouldn't call, there isn't a colloquial name for the kind of shape we're talking about, but I think we all have an idea that if I were to stretch this a little bit, I'd still get the number 2, even though there was something sticking out of it. So that was an amazing invariant discovered by Euler. Let me just see. I wanted to say something about that. Oops. All right. What if we did it to that shape? The surface of a duck. What do you think is going to happen? Yeah. 2. Good guess. Right. But I mean, is that what everyone would think you'd get? I mean, not obvious to you. I mean, it's probably going to be 2 because if I really put a lot of air in that duck and if I drew a farm all over that duck and then filled it with air and stretched it out so that it looked like a sphere again, I would just have a bunch of farms on the sphere. So this drove mathematicians to think about geometry in different ways. It led us to try to think about sort of seeing shapes through some kind of a lens where, this is going to sound kind of weird, where in that lens the shape of a rubber duck and the shape of a balloon are the same. We would have looked for a word like triangle that refers to both of these shapes. Well, I want to try this again because I kind of like this Farmville thing. I have a different kind of balloon here. Maybe you've never seen this kind. This balloon has a hole in the middle. Well, it's something that goes all the way through. So let's try. What do you think is going to happen if we break this up into farms and we make the same count? Does anybody have any guesses? Yeah.
We'll end up with the number 2.
That's a good guess. What about you?
I think we're going to get 1.
You think we're going to get 1. You think we're going to get 2. How can we settle this argument?
Try it.
We could do it. Yeah. Now, does anybody want to do it, or do you just want me to do it? Yeah, okay. I know you do. Hang on, let's see if there's somebody else. Does anybody want to do this?
Torrid.
What's that?
Is that what they call a torrid?
A torus.
Torrid. It reminds me of a Tesla coils.
Oh, yeah, I guess so. Yeah. I mean, mathematicians would call this, in topology, this is called a torus, or it's a donut. But yeah, that shape. What's that? Okay, you can do it. Here. We have to be... it's hard to draw. Well, I'm just going to make sure you do it right.
So am I doing fence posts or?
Yeah, just posts and edges and making it into pastures. But let's try to make all the pastures be like triangles or things. A pasture can't have a hole in it, so you can't have a.
So there's one pasture.
That's good.
I keep feeling like it's going to pop. And do another one?
Okay, yeah. I mean, let's connect it up and make one go. You need to make one go all the way through, I think.
All the way through?
Well, we can just pretend.
Okay.
Is there somebody skinnier that could? No, I didn't mean it that way.
Wow. Let's see. That would mean I'd have a...
Well, you can make some square ones and things like that. The thing you're not allowed to have, the thing you can't have is a pasture with a hole in it. So if you took the top of that, if you had a pasture that was like that, if the rest of the torus was out here and you had a pasture like this, that would be a weird kind of a field. That would be a field that had a hole in the middle, and we're not allowed to do that. Yeah. Do you want me to do it?
Yeah.
Huh? You're doing good. Okay, that's pretty good. That's good, actually. Okay, all right. I mean, let's call it a day. That's good. Okay. So, no, I think I want another one going.
If it's a flat plane, it does not come up.
I'm going to have to come around here. All right, I was a little vague on what I have to do, but I think I've got everything. I'm going to be just going to play it safe. All right, so obviously I didn't do this in advance, but I think that's pretty good. Okay. All right, so this is marked up in some way. You're just going to have to trust that we did it according to the rules. So how many pastures do I have? I have 1, 2, 3, 4, 5, and then a huge one, 6, and that looks like I've labeled them all. So that's 6 pastures. And now, how many fences have I got? I got 1, 2, 3, 4, 5, 6, 7, 8. Oh, I counted that one twice. 7, 8, and 9. So that I think if I did this right, I have 9 posts. And now, how many stakes do I have? 1, 2, 3, 4. Oh, I lost count. 1, 2, 3. I'm going to cheat. I think I must have 3. Somehow, this should have worked out, so I have 3. Okay. So sorry. I couldn't find, when I've done this kind of thing before, we had a big inner tube and it was easier to mark up, and this is hard to get through. But if I had done this and counted correctly, I would have wound up with 3, and the answer would have been 6 plus 3 minus 9, which is 0. So I would have gotten 0 for that. So that's kind of an amazing thing also. So no matter how, and once again, it doesn't really depend on the fact that was completely perfectly round. If I would have done it with this wobbly thing, that's close enough. I could have blown it up harder so that it was shaped like that, and I would have also gotten 0. So this is an amazing thing. No matter if you take a shape like this that has a hole in it and you break it up into farms and you make this count, you're going to get 0 no matter what you do. And if you do it on something like this, on a ball, you'll get 2. So that number that you've calculated, that number can tell you whether you're holding a shape like this or a shape like this. Or imagine, for example, that you're a creature that's living on some kind of a planet that's floating through space. I know what you're thinking. Newsflash, you are a creature living on a planet that's floating through space, right? But suppose you are on that and you wanted to know the shape of your planet. You know, if you could get enough people together to cooperate, you could calculate this number. And if you got 2, you'd know that the planet was round like a ball. If you got 0, you would know that it wasn't round, that it in fact had to have a hole in it. So we say that mathematically, mathematicians, what we say is that you can figure out the shape of a surface, even if you can't get off the surface and live on it. Doing that calculation lets you figure out, lets you know if your shape was round or if it wasn't. And in fact, there's something even more powerful. If I built something, I couldn't find any balloons like this, but imagine that I had a balloon, so these were piped together, that had 2 holes in it. If I did it on this and I calculated that number, I'd get -2. And if I had 3 of them, I'd get -4. And in fact, that number completely determines the shape of the surface, the number of holes in it. It's a remarkable number, and it's a remarkable invariant of surfaces. So when Euler, I think I got my slides out of order. Let me just, excuse me a second. Yeah, let's go back to the duck. So again, so mathematicians looked at this and we want to know what is it? I mean, imagine, so this is telling you about shapes, but it's also forcing you to try to think about geometry in a really new way. I mean, if you want to really understand what's so two-y about a ball, you have to say that, you know, a ball is just as two-y as that duck, and that's just as two-y as the heart that I had. There's something that it forced mathematicians to start thinking about geometry in a radically new way. And that led to many, many advances in mathematics. So I think I put up a bunch of pictures because I wanted you to try to guess, given these calculations. I wanted to hold up some different shapes, and I wanted you to tell me what you think we're going to get for this number if we played Farmville on these different shapes. So here's a bottle of bleach that I happen to have with me. It's like as long as it's less than 3 ounces, you can take it on an airplane. But, no, so what do you think you're going to get with this if you do it? You're going to get 0, yeah, because that has 1 hole in it. So you're already learning to look at shapes through this lens that the mathematicians learned. I mean, this took many, many, many years of mathematical development before people learned to look at shapes that way, to think of a ball or the duck as somehow having something to do with each other, or this shape, or here's another one. This says, creating solutions to reduce Kairos drinking among NU students. So this shape, what shape, what do you think you're going to get if you do this? What's that? Anybody? 0. You're going to get 0. Now this doesn't look like this at all, right? It's got an inside and out, but that inside, there's no more holes in it than just the 1. So you've already learned, you know, maybe you've heard this joke, you know, a topologist is someone to whom a coffee cup and a donut are the same thing. Maybe you've never heard that joke. Topologists are kind of weird that way. But anyway, now you've got the bug, right? In the sense of counting these numbers, a donut and a coffee cup are pretty close to being the same thing. So so that jug's not so different. Let me try a different shape. What about baby dino here at the beach? Not the kid, the dinosaur that kid's riding on. What do you think you're going to get for that? 2, right? You're going to get 2 because that's just like a sphere. But you're starting because of this. You've encountered this invariant. You encountered something mysterious, because I'm goading you into it. You're starting to see geometry through a different lens. This is what algebraic topology is, my field of research. We study the invariants of shapes that don't change, that are invariants of the kind of thing we're looking at. If I stretch them out and move them around, I want to count something about them that's not changing. And that's sort of what the field of algebraic topology is. I'm trying to figure out if I have another one of these things here. No, okay. So here's one of the spectacular things that Euler did when he first discovered this invariant. There are these idealized, these solids in mathematics called Platonic solids, and they're shapes that they're made out of faces that have the same number they're the same kind of faces. So this is made out of triangles, the dodecahedron's made out of pentagons, the tetrahedron's made out of triangles, the cube out of squares, the octahedron out of triangles again. There are so these were known to the Greeks, and they're called the Platonic solids, and they're the most symmetric solids that you can write down. And if we were to, but they're also, we can think of them as sort of the earth broken up into farms, right? This one has a pasture, and that pasture is surrounded by 5 fences, and there's stakes between the fences, 5 of them again. And so we know that if we were to make our calculation with these, we should always get 2. And when I made this, I always called them, they were faces, edges, and vertices instead of pastures, fences, and stakes. But it's the same principle. And if I were to count that for these, I'd get these numbers. And you can see that they all add up to, the numbers all add up to 2. So 20 plus 12 is 32, minus 30 gives me 2. I always get 2. And that, if you combine that, you combine the fact that that has to add up to 2 with the fact that all the faces have the same size and shape, and the same number of faces comes together at each point. If you combine those 2 facts, you get a system of equations. You get some equations that express that the same number is coming up at these points, and you get these equations that something's adding up to 2. And those equations are remarkably constrained. And what Euler was able to do with those equations was prove that they only have 5 solutions, that there's only 5 Platonic solids. So that was also kind of a remarkable proof of this result. And these are the 5 Platonic solids. So this invariant, even in the case when it was 2, had many powerful consequences. Okay, so looking at the time. So I spent some time. So what have we done? I wanted you first just to have the experience of an invariant without it being too technical. So you understand kind of what it feels like. You feel like there's something in control behind the scenes. And then I wanted you to sort of discover, along with Euler, an invariant of shapes that made mathematicians, and you, I hope a little bit, start to think about shapes in a new way. Start to think about what is this shape, what about this shape is, or what is this an invariant, is this invariant an invariant of? But mathematicians also interact with invariants in another way. Sometimes we have something that we want to study, and we want to know, we want invariants to help us study it. So we kind of backed into this thing with these balloons and the geometry, but mathematicians also, like, we might want to investigate something about weather or something about equations, and we might look for invariants. So there's one of these that kind of floats around in the early history of mathematics, and in about the 1930s it comes into force. And here's a way to kind of get into it. So this is something I downloaded illegally from the U.S. National Geographic Survey. It's a topographical map. You might look at a map like this if you're trying to hike someplace. And when a map like this, these circles, so that little piece there, that's saying that's 9,634 feet high. I guess that's probably what this is. And this is a little bit below that. And this is all, this map, this line here is all the points that are that high off the ground. And these are all a little bit lower. And so if you're here and walking here, that's not going to be as steep as if you're trying to walk. I'm sorry, I forget how you, no, I think that'll be steeper because these are probably representing the same change in height as that. And up there, by that 9,400 something, that's another one. And so you can think of making that map in a different way. You can imagine, let's abstract and think about it mathematically. Imagine I had some surface that was described by a function. This would be the graph of a function. And I want to draw the elevation lines, or the contour lines. What I'm trying to write down are all the points whose height is this number I called y2. Or I want to know, I'm looking at all the solutions to f of x equals y2. And that might be all the points of height y1. And this happens, this exact thing happens in maps, right? If I look on this map, you know, just off of here, the points that are about that high off the ground, that's probably that circle and one up there near that thing that says 9,400 something. There's probably two ridges there. And then as I get lower and lower down, these get bigger and bigger. But by the time I'm looking at all the points that are this high, I'm just looking at a single circular path. And I've represented that in a really idealized way in this graph, right? Way up near the tip of those peaks, the path that's that high looks like a circle, two circles, and the path down here looks like just one. So this is something that mathematicians are interested in because we want to study functions, we want to study equations, and there came this question, how can I look for any invariance? Is there something in the geometry of this that, is there an invariant that I could measure about the geometry of this that there's something that would make me think of this as one circle is the same as two circles, right? We discovered this invariant of balls, and it made us think about balls in a different way. It made us think of, you know, that if something's stretched out, as long as it doesn't have any holes in it, it's still basically a round ball. And I want to do this now. So mathematicians, especially around the 1930s, started wondering, is there something I can measure that won't distinguish between this and this, so I know that they could possibly be solutions of the same equation? So this seems like a little bit crazy. It seems pretty unlikely that we could find something that looks at one circle and looks at two circles and goes, yep, same thing. That seems really, really unlikely. But I want to pursue this a little bit. I can't remember. I think I didn't do that yet. So I need to actually draw on the board. Can people see this board okay? No, not at all. You can see it. I think it's hard to see in the back. I have another device I could draw with. I think it's okay. I'll draw on the board and I'll try and describe it. And so what I want you to imagine is a higher dimensional version of this. So one way that might come up is if I've got a bunch of heating coils, heating elements in a room that are in some weird configuration, and they're heating up the air in the room. And I'm interested in, now instead of the height, I'm interested in the temperature. So if all these things are, you know, if I've got something up there that's about 1,000 degrees and something over there that's also pretty hot, and then I want to know where in the room is it 100 degrees, well, that'll be some strange surface that's somewhere in between those 2 points. So instead of looking at the path where I'm a fixed height above the ground, I can look at all the points in the room where the temperature is the same. And what I get instead of a curve is I get a surface. Like if I had a candle, just a candle in the middle, then the surface, you know, the place where it'll be really hot in a roughly a sphere right near the candle, and as I go in, and it'll cool off as I get further away. So we have a name for these. These are called the isothermal surfaces, or in weather you call those isotherms. And so in that case, the isothermal surfaces would just be a picture of an increasing sequence of spheres. But something like this can happen. I mean, those all had the same shape, but the shape can actually change. So I didn't make an image of this, but what I want you to imagine, I'll try and draw it, and then I'll draw you I'll make a different picture of it. So I want you to imagine that I took some heating elements and I made them go around they were coiled up around a big area about the size of a donut. then if it was just that, then the isothermal surfaces would just look like donuts shrinking. As I got, the temperature would be roughly proportional to the distance from the heating element. And if I was at 1 inch from all the heating elements, that would just be a donut a little bit smaller. But now imagine that I also, so that's the thing I wanted to try to draw. So imagine I've got a big surface of these heating elements, and then at this point here, I put in some other strip that's also heating up the air there. So now what are the isotherms going to look like? Well, roughly, if I'm pretty close to this surface, the points that are pretty hot, that are pretty close to the coils, will look like this donut. And if I ask for where does it cool down, so where is it about half as hot as it is here? Well, if I'm far away from this coil, it'll just look like the surface of my donut, but just made a little bit smaller. But these things are going to stay hot. And so in order for this to cool down, I have to be even further away. So instead of like concentric spheres or concentric donuts, what the isothermal surfaces for this arrangement of heating elements would be, you'd have a donut and then you'd have a smaller one, and eventually there'd come a point where they would sort of break, and inside you would just see something that isn't quite a donut anymore. This probably. But something that's broken. So this inside is supposed to be a picture of just something that doesn't quite go around and connect, and it's sitting inside this bigger sphere. Do you understand that? Does that picture make sense? Do people see that? Okay, so I'm only looking at the people nodding. I can't see the people going. I can't see that. Okay, so that's kind of interesting. So we want to wait. So this actually breaks our rule, right? We calculated this Euler number, and we got 0 for the donut, and for this thing inside where they don't quite come together, that would have given us 2. So we know that this Euler number we were looking at is not an invariant of the possible shapes of isothermal surfaces. And mathematicians really wanted to know these invariants. They wanted to know if there were any. And in the 1930s, a mathematician named Pontryagin kind of turned this corner on his head, and he said, well, I guess I don't really, maybe we don't know what the invariants are, but let's try to group surfaces together in this way. Let's try to see what lens it would make us look at geometry through, and see if that makes us invent any new geometry, and see if maybe that will help us think of invariants of equations, or tell us things about no matter how you put the temperature in a room, the isothermal surfaces have to have some property. So in order to do that, I want to explain geometrically. Let's forget about temperature, let's forget about all that, and think about geometrically what happens as I pass in, as I look at the surfaces where the temperature is cooler and cooler. And what's going to happen is that there's this circle around it. So I drew the circle around there. And at some point as I move in, the surface, you can think of it getting cut open along that surface, or along that circle. And disks are glued in at the place where it was cut. So I drew the geometry different here. I imagine that I cut the surface open and glued in 2 disks. So this is a maneuver that became known in mathematics in the 1960s as surgery. But Pontryagin invented this in the 1930s, and it was a really important maneuver. It turns out, not just for solving equations, but it turned out that many, many things one wanted to know about geometry, that you could take many questions about geometry and you could convert them into problems about understanding surfaces up to surgery. So now, we want to know right now, are there any invariants of, could we change this Euler number? Is there some other number we could take about a surface? Is there something we could do and calculate a number that wouldn't change if the surface changed by surgery? Well, one way of answering that question is saying, well, can I get from any surface to any other surface by surgery? If I can do that, then there won't be any number. They'll all be the same as far as that's concerned, and there won't be such a number. So let's change the question again. Can I get from any surface to any other surface by surgery? Now, I've kind of led you to believe that the answer is yes, because I've only shown you two surfaces. There's a donut shape, and there's a sphere, and there's a picture of going from the donut shape to the sphere using surgery. But there's a lot weirder surfaces than that, especially if you allow them to pass through each other, and that's what I want to do. So, can anybody think of a weird surface that like is constructed because it passes through itself? You got one? A Klein bottle. That's good. That happens to be the same surface I was thinking of. Right. So there's something called a Klein bottle. So here's a really mathematical drawing of a Klein bottle. You're supposed to take a long tube and you're supposed to bend it back around and pass it through itself. So as it gets down to here, it looks like two tubes, and then you connect them together. So that's a very mathematical picture of one. That's a Klein bottle. There's one actually made out of glass. I think that's what the internet said. And so a Klein bottle is kind of weird, right? If you poured liquid in here, it could go back up there and sit in this part, but it wouldn't really have gotten inside or out. In fact, inside and outside a Klein bottle doesn't really make any sense. Oh, there's a Klein bottle filled with liquid, and you might wonder, what would you do if you had a Klein bottle filled with liquid? Well, you could smoke a cigarette and pour beer in it, I guess, like that guy. So, all right. So let's take a Klein bottle, and now the question is, can I turn a Klein bottle, that's a weird surface, can I turn a Klein bottle into a sphere using surgery? Does anybody have any opinions on that? Do you guys get this surgery idea? Sort of, yeah. We see that really in that handle there, the only thing you actually feel like interacting is like grabbing that handle. What if we were to just do surgery right there? So let's take a Klein bottle. Let's take a... That's okay. I have a question though. Is that your ringtone?
No, this is a reminder, Mama.
Oh, okay. All right. Okay. No, it's fine. I just I wanted that if that was a ringtone. That was really good. All right. So here I'm drawing a picture of a Klein bottle, and it's coming through itself, and so that's supposed to kind of look like that. And I want to do surgery right here. Here's a circle sitting on the Klein bottle. And what does it mean? How does surgery work? You cut the Klein bottle, you cut it open along that, and then you glue in discs. Okay, so I just cut it open and I glue in two discs. I didn't draw that very well. This is supposed to be that's supposed to be a disc. Now, imagine just filling this up, being in there and filling it with air. As you fill it with air, this is going to stretch, and it's going to pull this back through the surface. And as it does that, it'll eventually flatten out and become round. So at some stage, it might just look like this. Let's see. It'll look like that, but that's just a ball that's been pushed in at some point, and so that could slowly move out until it was just a regular round ball. So I can do surgery on the Klein bottle and get the ball. And that starts to make you think that I've been spending the last 15 minutes telling you a big theory of nothing, because it starts to make you think that there can't be an invariant, that, I mean, if we knew something, like if we knew that in any mountain range, the points that had the same height the paths, that they had to have a very special geometry. We'd have heard about that by now. But that's not, those can be, they have to be circles, they can be many circles, but there's nothing else special about it. And they could be 2 circles, or at another place on Earth they could be 1. And if we try to do this with isothermal sheets or more general solutions to an equation, we're starting to get the idea that no matter what we did, we might not, that there isn't anything special about, in other words, I could get from any surface to any other one by surgery. And this is exactly what Pontryagin thought. In fact, Pontryagin wrote a brilliant paper in the middle of the 1930s. It was announced at like the Olympics of mathematics, something called the International Congress of Mathematicians, but Pontryagin was in Russia and couldn't leave at the time. The paper was presented by somebody else. And later, Pontryagin found a mistake in this paper. And there was very little communication between the East and the West. Pontryagin found a mistake, and he corrected it himself. And a mathematician who actually used to be a colleague of mine at MIT, George Whitehead, in the 1940s, also discovered Pontryagins' mistake. And correcting Pontryagins' mistake and finding the invariants of surgery led to enormous advances in mathematics. So this simple invariant, in this exact case, led to enormous advances in mathematics. So let me show you a surface that you can't cut up and turn into a sphere. And I was going to build a model, but I couldn't find the right materials for it. So I'm just going to tell you how to do it. So let me first, so here's how I might imagine building. So the surface is it's kind of like a donut. So how do I make a donut? Well, mathematically, I could take a piece of paper. I would take a piece of paper and I would make it into a loop. Well, if it was made of rubber, then I could stretch it back around and glue it to itself again. And that would make the surface of a donut. Now, what I want to do instead, every time, is instead of just attaching it to itself, the paper's allowed, the paper's allowed to pass through itself. So I'm going to, instead of just making a circle out of it, I'm going to pass the paper through itself. This is going to be hard to see. I want to pass it through itself so it makes a figure 8. Okay, so this sheet's connected to this one. These 2 sheets are connected. And when the paper passes through itself, it makes a figure 8. But it's really just a tube, but it's a tube that's been twisted up when it went into space. And then, instead of just coming straight around and gluing the edges together, I'm also going to make a figure 8. So I was going to make a model and I didn't, but I did make a picture of it. So this is what it is. So that's a piece of paper or a piece of rubber glued to itself and then cut around and made into a figure 8. And this surface, you can't do anything to it. You can't do surgery on it and get it in and turn it into a ball. So this is something that's it's hard to think of. Pontryagin, a professional mathematician, didn't think of it, and it's something. So that tells you somewhere there's an invariant of surfaces up to surgery that will tell you that this is different from the ball, but it won't distinguish between that donut and a ball. It's kind of weird to think about it. And there's a fairly simple formula. Well, it's simple. I didn't give it to you. There's a formula like the one I was doing with the Euler characteristic, but it involves adding up complex numbers, and it's sort of a little too, I think, it's not hard, but it's a little too advanced for just a general public lecture like this. Okay, so the missing invariant of this was called the Kerver invariant. It was rediscovered by Michel Kerver in the 1960s, and it became a very important problem in mathematics to figure out when in dimension 2, this is a surface whose Kerver invariant, if we calculated it, would come out to be 1, just like we got 0 for that or 2 for that. So that's an important, so this is an example of a surface of Kerver invariant 1. In fact, on surfaces in space, up to surgery, there's exactly 8. There's 8 surfaces. There's 8 magically different surfaces, and they're all kind of weird looking. You don't really run into them. I mean, I don't, you know, it's probably hard to call up some manufacturer and get them to build this because it doesn't sort of, it's not used in any places. So there's a funny way to put the Klein bottle in. This is a surface. This is a picture of something called Boy's surface. It's in that's in Germany, in Oberwolfach, outside a mathematical institute called, we just call it Oberwolfach. Anyway, it's outside the Math Institute there, and there's this wonderful sculpture of what's called Boy's surface there, and that's another one of the 8. And in fact, this is a picture I drew of Boy's surface, but let me not, I'm not going to take time to go through it. So Judy referred to this book that a group of graduate students here and I are writing, and we're writing a book about this classification of eight special surfaces in space. But just to let you know, I mean, this invariant, it went on to be, I mean, this was a theorem that I proved with Mike Hill and Doug Ravenel in 2009 that says this thing I'm showing you with surfaces is very special in all of geometry. It can only happen in dimensions 2, 6, 14, 30, 62, and we don't actually know if it can happen or not in dimension 126. Maybe none of you have any opinions about that. If you do, let me know. But so these numbers, the pattern of these numbers is that they're 2 less than a power of 2. So 2 is 2 less than 4, 6 is 2 less than 8, 14 is 2 less than 16, but there's only these 6 possible dimensions. So this was a problem that it was there's a lot of math questions like this. This was an innocuous, weird question in one part of mathematics that people kept bumping into in completely different parts of mathematics. And so this was a problem in geometry in Pontryagin's era, and it was sort of the source of a famous mistake. And it became a part of homotopy theory in the 1960s, and my own thesis advisor spent most of his life working on this problem. And I sort of felt like I hit a baseball through Mr. Wilson's window, because I didn't really want to solve the problem that he'd spent his whole life working on, and I kind of accidentally did. But okay, so I'm going to stop here, and I just want to summarize a couple things, or talk a little about what I hope to accomplish. I mean, one thing is I wanted to talk about some real mathematics that real mathematicians think about, and this invariant and this surgery is something that mathematicians really do think about. But when I talk to people about math and I start explaining things, I often get this reaction, that sounds really important, but I don't get it. And nobody ever turns on a song on the radio and says, I don't get it. Well, it might be Miley, what's her name, singing about a wrecking ball, and you're like, I don't get it. It might be, but you don't feel like there's something about the experience of the music that was completely alien to you. And the other thing, mathematics should be that way, and mathematicians are we haven't traditionally been very good at conveying that, but I think there's ways of experiencing, of hearing the music in mathematics, there's ways of experiencing it that we all experience that mathematicians just haven't been good at identifying for you. And I think that magic trick, the terrible David Copperfield trick at the beginning, is exactly the experience. I mean, that's something where you're going through, there's a narrative, there's something happening, but you have a sense that there's something hidden from you that's very systematic. And this is the engine that drives mathematics. This is the notion of an invariant, and it's led mathematicians, even in these are real examples I described to you. It led mathematicians to see geometry in radically different ways, to think about solving equations in radically different ways, and it's led to questions that many of which still remain open, and like that darn thing in dimension 126. But so anyway, I hope you got a little bit of that out of this hour we've been together. That's all I have. Yeah, it was plenty of time. Yeah.
So we have some time for questions, and we have a mic because they're live streaming it, and so we have to use the mic.
Oh. had another balloon. Huh. Forgot.
Yeah. All right. So now we actually have time for questions, even though it took me a while to turn on the mic.
I'm sorry, I'm not a mathematician, but in the reality, is there only, in the law, only one surgery?
I'm sorry, in what?
You're only allowed one surgery
in moving from one surface to another? No, you can do it as many times as you want. So if I wanted to make, if I had a surface that had 2 holes in it like this, I could do surgery over here and then that would get it back to, then it would look like this with two little handles coming out, and then if I did surgery again, I could turn it into a ball. So no, you're allowed to do as many surgeries as you want to get from one surface to another. Yeah, that's a good question. I should have. Was that the question you? Yeah. You're allowed to do as many as you want, and yeah, okay. You can, yeah.
I hope this isn't a dangerous question, but what happens when you turn the surface? Because you're talking about a sphere or a donut, which has an inside surface, an outside surface, and then you were talking about the figure 8 tubes, and my mind immediately jumped to a Mobius strip.
Okay.
Is that a correlation that just can't exist, or is there some correlation to?
No, these
infinite?
Mobius strips exist all over the place. Like in this wire, in this sculpture, every one of these strips is a Mobius strip. But these Mobius strips, so a Mobius strip goes around and it makes a half turn before it gets glued together, right? That's the Mobius thing. But some of those are twisted 3 times, and some of them are twisted 5 times. So those, in fact, yeah. So that's the structure you have to start looking at to find this Kerr invariant. You have to start looking at, you have to look at little pieces of ribbon sitting on the surface and the number of times they twist. So that wasn't a dangerous question. It was a really good question, and that's the structure you have to start. You have to start looking at how twisted the surface is to measure this.
I guess what I'm wondering is, does it screw with your formula once you start making a twist? Because you go from one or two surfaces, or 2 surfaces, 2 edges, to 1 surface, 1 edge. I mean, does it throw a monkey wrench in what you're trying to discover?
No, you mean in the Euler formula or in the? No, the Euler formula. I didn't show you any surfaces like that, but the Euler formula also works for surfaces like that. Yeah.
You can't blow a Mobius strip up into a sphere.
Right.
So I'm not a mathematician either, but
that's good. Yeah.
I work with computers.
Unless you meant like me. You know,
I work with computers a lot, and I know a lot about the way that programs function. For example, when you compile a program, the compiler computes invariants of that program's execution states. And cool. I know that we use invariants all the time to reason about properties of programs. So what I'm interested in is, in mathematics, what is the process by which you find these invariants? Is it serendipity, is it art, or is it systematic?
I mean, that's a fantastic question. So sometimes it's like you said, it's just serendipitous, and I think that's what Euler was doing. I think he had a balloon like this. I forgot I had another balloon that's meant to be sat on, but I didn't have anybody. No, I think his discovery was serendipitous, but who knows? You know, Euler was an amazing genius. Sometimes it's by art, but sometimes, like in Pontryagin's case, it's hard to explain this in plain English. So I'm going to say it in a slightly technical way. What Pontryagin did was he defined what we would call an equivalence relation on surfaces. So 2 are equivalent if they're the same up to surgery. And then he tried to use other means to just compute how many there were. And what happened is eventually there were techniques coming from a different part of mathematics that let you make that computation. And then once you had the computation, you knew there were 8 of them or whatever, and then you could go back and look for the invariant. So sometimes that I suppose is something I would label sort of just art. I mean, that's the sort of artfulness of it, that you can sometimes turn the question on its head, and in simple cases compute everything. I don't know if that's sort of how it is, but but often other places where I've personally discovered invariance, it's from suddenly having an insight into how something works, or suddenly realizing I'm looking at this in some way and ignoring a lot of I'm saying this is all noise, this is important, and then I suddenly see an invariant. But
yeah, so another question that you brought up in my mind was that in computing, at least, sometimes we have invariants that are sort of fundamental. They describe these really important properties of the computation.
Yeah.
But other invariants are boring. Like, for example, when the program is at the first line before it started doing anything, all the variables have a value of 0. That's an invariant of it's like there's an implication there that's describing the invariant. So, do you find that there are uninteresting invariants? And if so, how do you navigate this space or filter the uninteresting ones out and get to the interesting ones?
So I don't have I mean, there's invariants like that you described that are like just a basic reality check. Let's just check a stupid invariant to make sure everything's, as you said, starting, all the variables are 0 so that it's starting right. There are a lot of situations where you have, like in high enough dimensions, I can compute a lot about these spaces up to surgery, and the aggregate of information I get, I can make a complete calculation, but it's a meaningless aggregate of information. There isn't any system seen in it yet. And then what almost always has to happen is somebody has to bump into the same thing from a different point of view. It must be the same in computer science. In fact, I have a friend who declared that any computation in mathematics anybody did is wrong unless somebody else did it from a completely different point of view. And so I think that's what usually happens. A lot of them, I mean, sometimes you can, like this 8 was discovered, in a way I can't explain, sort of in a very computational way, and then people looking at it and kind of reverse engineered figured out how to think of it in terms of strips. And that was a situation where you could reverse engineer from an answer and find something beautiful to say. But the general, it must be the same in computer science. The general thing is that somebody needs to bump into it accidentally for a different reason. Well, I don't know, what happens in computer science?
Well, we try to compute invariants,
of
course.
Yeah.
And usually the ones we can compute are simpler ones. They're not the deeper ones that give you real nice insights. Those have to come out of people's heads. So.
No, that's cool.
So this question comes from a professor in Hamilton College who is watching via the live stream. She asks, is there an analog for surgery in homological algebra, since we steal so much from topologists?
Yeah, yes. Oh my goodness, yes. But that's a sort of technical, that's a good question. Sure, there's an analog of surgery in homological algebra, but I can't, of course, really, she should write me or something. I can't really explain it. But where there's a direct analog of surgery is in studying quadratic forms. So, you may have, you learned this in sort of high school or maybe a little after. If you draw x squared plus y squared equals 1, that'll be a circle. If you draw 4x squared plus 3y squared equals 1, that looks like an ellipse. But if it's x squared minus y squared equals 1, suddenly it looks different. It's a hyperbola. And sometimes you get a parabola. You either get an ellipse, a hyperbola, or a parabola. And that's classifying quadratic equations, or what we call quadratic forms. And a classification like that exists in higher dimensions. And for reasons I can't quite explain, there's a there's a very strong analogy between shapes, surfaces, and quadratic forms. And there's a notion of surgery on quadratic forms. And amazingly, sort of in the 1960s, the people who were working on geometry developed such amazing intuitions about quadratic forms because of this that they were responsible for some real revolutions in the field. And in fact, John Milner, who was the same Milner, his name came up, I think his name came up earlier. Anyway, oh, that was maybe in an earlier lecture today, sorry. John Milner, who was one of the real architects of the modern theory of much of modern geometry, I mean, he made some important conjectures about pure algebra, about quadratic forms in the early 1970s. They were called the Milner conjectures for some reason, and those were eventually solved by Vladimir Voevodsky in the late 1990s, and he was awarded the Fields Medal for that, which is the highest. It's like the Nobel Prize in mathematics. So in homological algebra, yes, they do come in, but the place that they really change the way you think about something is in studying quadratic forms, and that's a beautiful story that continues to grow today. In fact, I'm doing one of my current research projects now is on a relationship like that. So yeah.
I feel like I should go to that side of the room. Are there questions on that side of the room? Okay. Then there was a question over here somewhere you were pointing, Alex, or no? No? Okay. Well, that's all actually just fine because we should go ahead and wrap this up. So let's, sorry, let me come up here. Let's say thank you again to Mike Hopkins.